topic I have chosen is enormously broad, and I realise that there's far more than I could talk about in 20 minutes. So it's partly about what I've cut out, but that's the euphemism for I'm leaving plenty for questions. So many of the things I may not explain as well as I would like, or as fully as I'd like, I'm giving the opportunity for people for us to elaborate on in the questions afterwards, if you wish. Okay, so thank you. I wanted just to give some insights or ideas about some of the things that have been going on in testing many of the most fundamental parts of science, of geology, plate tectonics, which is this grand unifying theory of the earth sciences, and the fact that there's actually quite a lot that is not known, quite a lot that is quite questionable, in fact, or based upon extremely shaky foundations. And just give you some ideas of the research I've been involved with at Cardiff. Part of international teams, of course. You don't do any marine work by yourself. You wouldn't get very far on your own in a boat. So these are all part of big international collaborations that I've been involved with. But just to give you some ideas, some insights, I think, into the complexities of what we now know are going on behind some of the basic fundamentals of plate tectonics, particularly with regard to the ocean floor. Right, let me get. It's doing it doesn't want to turn the page yet. Why does it not want to turn the page? Just a minute. Okay, try again. Okay, good. All right. Okay, some basic precepts of the textbook view of plate tectonics, I think, if you like. We know from 40 years, 50 years now, 60 years even, of I'm particularly going to talk about divergent margins or mid-ocean ridges, where oceanic plates are formed and create plates. So the plates are pulled elsewhere by subduction that drags them down into the mantle, the oceanic plates are pulled apart and make new lithosphere. Now, this is a very fundamental process. It makes up 2/3 of the surface of the Earth, and therefore is one of the most fundamental parts of the plate tectonic cycle. So, under these plates, they move above a solid but plastic mantle. The mantle can flow, but it's solid, and that's one of the misconceptions that people often have. They think that because the mantle can flow, it must be a liquid. But if you think of it instead of iron taken out of a forge, it's still solid, but it can flow. It's bendy, it's ductile, it's plastic, and the mantle is of the same properties. When it's at about 1300, the mantle of this rock called peridotite is predominantly olivine. Which is the gem version of olivine is called peridote, hence the rock could be peridotite, and that is the most common rock on Earth, as it makes up the whole of the mantle. Okay, that's just that little bit of background then, and then from broad plate tectonic theory, we know that the continents move around, they're pulled apart. The ocean lithosphere is formed at mid-ocean ridges and destroyed at trenches. So that basic idea of plate tectonics, don't worry, I'm not trying to trash the whole of plate tectonic theory. That would be unwise in the extreme, but I just want to explore some of the details of how we think that ocean lithospheres formed at mid-ocean ridges and show you actually there's a lot less known than you might think. It covers 2/3 of the surface of the Earth and is responsible for about 2/3 of all the world's volcanism, of heat transfer, and So it's a fundamental importance to know what that process is. It is also very important for seawater. So the entire volume of the world's oceans is circulated through cracks in the ocean lithosphere and out again every less than 1 million years. Some of it at the hot black smoke events, where the laden waters are expelled into the seafloor at about 300+ degrees centigrade, but much more sort of diffusely across much of the ocean basins. So there's a very profound control on the composition of seawater, and through subduction, pretty much all of the ocean floor is recycled back into the mantle again every couple 100 million years or so. So it's a very fundamental process. Okay, so people are more or less familiar with this. Just a few very brief background. I don't want to get into the sort of a history of plate tectonics or all of the theory behind, or the data behind how we know about what the ocean crust is, but I do want to emphasize a few points. Much of what we know comes from seismic experiments. These seismic experiments have been across much of the ocean basins, much of it done after the war. There's a lot of explosives left over, so they used them to send seismic waves into the seafloor, the subsea floor, and back again. And they determined that the ocean crustal structure is remarkably uniform. It's different from the continent, but in the oceans, the crustal thickness there is typically about 7 or 8 kilometers only, and there's a very distinct boundary to mantle velocities underneath. So the ocean crust is not the same as the continental crust. So that much of the seafloor is underwater is because it's different type of crust from the continents. Okay, so the point I wanted to make about the seismic structure, the internal structure of the ocean crust from these seismic experiments, is that it's extremely simple. It layers increasing velocity downwards to a sort of tick increase where the mantle, we go down to mantle velocities. But the layered structure of the crust itself is very simple. It's everywhere is the same across the ocean basins. The world over, you see exactly the same structure. It's about 7 kilometers thick, and it has lower velocities at the surface, getting to uniform velocities below this Moho, or this sort of increase to mantle type velocities. The boundary between the two is regarded as the boundary between the Earth's crust and the mantle. Okay, and we know that's the case because it says so on Wikipedia, but all seriousness, being more serious about it, this has been a fundamental sort of acceptance that this boundary represents the base of the crust beneath the continents and beneath the oceans, but beneath the continents is about 40 kilometers thick. Okay, so the seismic structure of ocean crust then shows this very regular velocity structure. And it's the same everywhere, irrespective of spreading rate. So the rate of seafloor spreading in the Atlantic is maybe 2 centimeters or less, 3 centimeters. In the Pacific, it can be up to 15 centimeters per year or more, but we see exactly the same seismic structure. So that's been taken as a fundamental concept, that ocean crustal structure is therefore very simple and it doesn't change with spreading rate. As to what that structure is in terms of rocks, well, we still don't have much direct evidence from the ocean floor themselves. We haven't been able to drill holes all the way through. It's far too, it's very technically complex and expensive, and I will show you later on of our most recent attempts to try to do this. And so much of our understanding of ocean crustal structure and rocks comes from ophiolites, which are on-land fragments of what we believe to be ocean lithosphere stranded in mountain belts and representing closed ocean basins. They show a regular internal structure with prototypes typical of the mantle at the base, and then gabbroic rocks, which are coarse-grained rocks of basaltic composition, sequences of dikes, vertical sheets of dolerite, pillow lavas, which are characteristic of seafloor extrusion, and then deep water sediments on top. So you take samples of each of these and measure their velocities, and they more or less correspond to what you get from the seismic layering. So it's from the late 1960s onwards, it was taken more or less as a consensus without any further examination that this is what the ocean crust is made of. And we then come up with these very simple sort of layer cake models for ocean crust, and the idea of this conveyor belt, plates are pulled apart, magma chamber beneath the crust, and this splits periodically to form the new ocean crust formed, and the two sides are moved apart. And the lower crust, as per the picture there, is made of a slowly cooled version of the same basalt. Okay, so all well and good, and this is what's in the textbooks, and this is what most people are taught, even at university level. The problem is that in some places that doesn't quite work, and we have sort of for quite a long time pushed under the carpet the places where we don't get what we expect by this simple model. The most awkward evidence, if you like, is the fact that in many places that you actually dredge up mantle rocks on the seafloor. So these mantle rocks now are not the peridotites, the olivine-bearing rocks that you see, but they're a nasty mess called serpentinite. And serpentinite is basically, serpentine is what happens when you get water at olivine. Olivine's very unstable in the presence of water, and it reacts and sort of basically puffs up like popcorn to suck up to 13% water, and it turns into this this mineral called serpentine and the rock called serpentinite. It's often very nasty looking, as you can see from the dredge rocks that we brought up here. It shouldn't be there on the seafloor if we've got 7 kilometers of ocean crust on top. And that is a very difficult question to answer. It's not, the more we're exploring the mid-Atlantic ridge or the Southwest Indian ridge, the more we're finding this, more of this material present. So it's not easy to explain by the standard ocean crustal model. And don't forget that the lithologies that we were, the ophiolite analogy is only an inference. We haven't actually drilled through the ocean crust to be able to see what actually it's made of. So it's not necessarily, the assumption we've made is a very simple one, and actually there could be a lot more going on. So, the more we've been investigating, the more we've been finding that it doesn't work in detail along slower spreading ridges. So in the top right there, the diagram shows the spreading rate of the ocean floor coded by color. So the blues and the purples are slow, what we call slow spreading ridges of less than about 5 centimeters per year. That covers the Atlantic and much of the Indian Ocean. In these places, we quite often find these serpentinites. And when we go in detail, we take submersibles down or remotely operated vehicles, we can actually find that the serpentinized prototypes are exposed on the seafloor at the ridge axis. So they're not simply being pulled apart on faults, although more of that in a moment. So we find them at the seafloor, and we find them in places sitting with pillow lavas sitting directly on top of them. Don't expect you could be able to see anything very much in that seafloor picture. That is one of the problems of trying to use submersibles to investigate or map the seafloor. It's a bit like trying to map Snowdon at night with the torch. That's about as much as you see out of the window. But anyway, the observations we have are telling us that sometimes there is no crust there. We just see, or no lower crust at least. We seem to see mantle on the seafloor. Importantly, those places may be ones in which they have normal seismic structure. They show a 6 kilometer, 7 kilometer crust in a Moho, according to the seismic refraction profiles. So something is very wrong. Okay, so we have serious problems then with these models at slower spreading ridges. And this is where I could diverge for another half an hour easily and to talk about some of the research we've been doing on trying to work out why we see mantle on the seafloor. And in very, very short summary of that, we see enormous geological faults, normal faults, extensional faults, which such as this fault plane here, which is 9 kilometers long. Sorry, it's 9 kilometers in that dimension, and here's the Atlantic Ridge. And these faults, these enormous structures are just pulling the plates apart. They're low angle, they have enormous displacements. So we're now realizing that at slower spreading ridges, we get faults as an important part of the seafloor spreading process. And doubtless that is partly why we're seeing the mantle on the seafloor. But again, these are places that have normal seismic velocity structure. So how can we possibly have a Moho, which is supposed to be the crust mantle boundary, at 6 kilometers below the seafloor when we've got mantle on the seafloor? Okay, so this is how do we explain this? And in fact, actually, it's interesting that the person who first proposed seafloor spreading as a concept, Harry Hess, he originally in his idea suggested that this ocean crustal layer, the seismic layer, was actually made of serpentinite, because serpentinite has velocities because it's taking up water in the lattice. The density drops and the velocity drops. And in fact, serpentinite has the same velocity as our gabbro. So you're going to have, if layer 3, taken as the lower crust, has a velocity of about 6 kilometers per second, actually, partly serpentinized peridotite can also have a velocity of about 6 kilometers per second. So in fact, what we have been living with for 50 years is one interpretation of what the seismic velocity structure represents. So it could be gabbro, the lower crust, layer 3, but it could equally well be partly serpentinized peridotite, actually as Hess proposed back in 1960. So the problem is that we've based all of our idea about how uniform ocean crustal structure is and how uniform the seafloor spreading process is, this conveyor belt, and we've based it upon the fact that we have equated the seismic velocity structure with gabbro as the lower crust. But actually, it could be either one or the other. And so it could be the Moho might not actually be the crust mantle boundary at all. So this step increase to mantle velocity structures that we see at 7 kilometers depth might actually be the lower limit of which seawater can penetrate down into the mantle and actually change peridotite into serpentine. So that might be the upper temperature limit of serpentine stability, which is about 400 degrees. Or it could be the limit at which you keep cracks open and can get water down that depth. So all of our preconceptions about how uniform the ocean crustal structure are basically quite bogus. We don't know how much we can now take our original models for crustal structure and how far they apply. It could be that across most of the ocean basins it's still correct, it probably is, but significant areas it may well be something completely different. It might be that there's no igneous crust there at all and you've just got altered mantle, or it might be that you've got half and half. You've got if you like, a plum pudding of gabbro intruded into peridotite, and that this varies along the strike of the ridge axis. We just don't know, and we can't know unless we ground truth it. So this is where we can't use geophysics. We now need to drill. We now need to get direct evidence, geological evidence, to try to determine how uniform or otherwise ocean crustal structure is. So we have, this is the premise behind some work that I initiated in the Indian Ocean along the ultra slow spreading ridge at a place called Atlantis Bank, which is a one of the sort of the footwall of one of these giant faults that are on the seafloor, adjacent to a transform fault. It's called Atlantis Bank, and it exposes gabbros, lower crustal gabbros on the seafloor. But we have and we used seabed rock drills, which are like on-land rigs, but on a very long extension lead, which you can drop down onto the seafloor and pogo around and drill lots of holes. And so we mapped this area. We found gabbros, we found prototypes as well. We found mantle rocks down there on the seafloor. Okay, so here on the top right is one of the cores that we recovered from the seafloor. That is a partially serpentinized prototype. You can see the veins where the water's come in and altered it to serpentine. Yet we still have a Moho at 5 kilometers depth. So this we thought was an optimum site to try and drill down. We can start halfway down because we have no upper crust there, to start to drill a deep hole to see if we can work out whether or not the lower crust, the seismic lower crust, is actually just serpentine, whether it's gabbro or whether it's somewhere in between the two. And that's the sort of the premise that it took us 20 years actually to finally get agreement to have the drill ship from the International Ocean Discovery Program to go and try and test this idea. So I could spend hours talking about our adventures a few years ago now in the Indian Ocean on the Georges Resolution. Suffice to say, it was an adventure with plenty of highs and lows. The technical challenge of trying to drill under these conditions to these depths is these water depths. These depths below the surface are extreme, and the engineering challenges are things that we're nowhere near yet able to solve. Here, for example, are the drill bits that you use. So you drill, you lower a drill pipe down on the, and you have a small hole in the middle into which you're supposed to be taking a core, and you drill around that with these roller cones. Well, quite often you come back without any cones, in which case, if you've left those very hardened tungsten carbide cones in the bottom of the drill hole, you can't drill through them unless you can fish them out somehow. And that involves a very sophisticated game of with dangling magnets down the hole to try and pull the bits out. That cone took about $300,000 worth of ship time to recover. But nevertheless, we got some extraordinary samples. This is the longest piece of igneous core ever recovered from the seafloor in one piece. And all of it was in gabbro. So we haven't yet hit mantle rocks. We've got to about 800 meters below the seafloor. Quite a few issues with holes collapsing, having to pull bits out of the borehole and cement the holes and things like that. But this again is part of the challenge of how we can drill deep below the seafloor. In truth, we need technological developments to go alongside the scientific developments and the challenge of going deeper. And as it stands, the hole is ready to reoccupy and go deeper. We now need to get the ship, which is currently on the wrong side of the world. And so that's the next challenge, is to be able to get the ship back to carry on and re-enter the hole and go deeper. So we haven't yet answered the question, which is a big letdown for those of you who wanted to know the definitive answer yet. But I hope it's illustrated how it is and why it is that we are spending money and effort to go and study these places, and why particularly we decided to drill a particular hole in this place. As with all of these studies, and this is my penultimate slide, you often come up with things you didn't expect. And we took some microbiologists on board because serpentine of prototype does involve the release of hydrogen, and that is food for microbes. And so it's been shown that the alteration of seafloor prototypes does potentially have implications for biomass. There are huge communities that could potentially live off this serpentinite seafloor if we've got serpentinite seafloor over a quarter of the surface of the Earth, then that's very significant yet. So what we didn't expect was that we would find microbes in solid gabbro. So these are crystalline igneous rocks that are crystallized from a melt, and they contain substantial evidence of microbes living within the rock, within the crystals and between the crystal boundaries. There are fungi, and there are archaea, and there are bacteria, some of the very, very primitive parts of the tree of life. But they are in quite large proportions in the igneous ocean crust. Together with those parts of the subsea floor that could be serpentinized mantle, potentially we've actually got more life locked up in the solid rock of the ocean crust than we have on the rest of the planet put together, which is quite a scary new thing to find out. Obviously, this is part of just a very new field as well. So if I just conclude then by this very brief snapshot, I hope has given you an idea of how we know a lot less about seafloor spreading. We know a lot less about plate tectonics than we thought we did, which for some is exciting, for others is uncomfortable. But I hope you can get an idea that this is shows that we have an awful lot to learn yet. It's a challenge to do that in these environments, and it covers all sorts of disciplines and all sorts of traditional subjects. So nevertheless, we need to work as teams, of course, to try to solve these things. We're none of us expert in all of these. So the picture at the bottom there is one of our seafloor cores, which actually shows that not only does serpentinization result in formation of conversion of olivine into serpentine, so the green background is serpentine, but these veins cutting through are carbonate. So the serpentinization reaction also fixes carbon from the seawater. So actually, the serpentinization of the seafloor, which could be 25% of all ocean floor, could be 6 kilometers thick beneath the seafloor, of maybe 13% water in the serpentine, but it also fixes carbon. So there's a natural carbon sink, which is completely unconstrained and unknown part of the carbon cycle. So we're actually now getting into things that are far different from discipline, actually thinking about global budgets for the whole of the Earth system. So it's really important that we know and understand this really poorly understood, neglected part of the system. So I shall leave it there. I shall point you towards my website, seafloorspreading.com, which on which I have quite a lot of resources relating to things I've talked about, more about the faulting on the seafloor, which I would love to have spoken to you more about. At the moment, as of today, as of November 2020, the site has been taken down because we're having an argument with the web host over whether or not we've paid a bill or not. We have paid a bill, but they haven't received it. So anyway, the site is currently down, but it should be back up again pretty soon, and I hope it won't disrupt anybody. Otherwise, I'd be happy for people to get in touch. And now, of course, to answer some questions. Thank you very much.
Thanks a lot, Chris, for that really interesting talk about some really fundamental aspects of geology at the Earth's scale, the whole Earth. So as usual, I think we've got some time now to take some questions. So please use your type your questions in the Q&A panel, and then I can read them out for Chris. I think, Chris, well, it's really up to you. Perhaps you could stop sharing your screen and reactivate your video.
Right, we are. Okay. Now then, stop share. And no, go away. Not you. So share. What do I do to share now? Right, am I back again? No, I'm not.
No, not quite yet. So you shouldn't share, which I think is okay.
Right, okay, stop share again. Right,
Um,
okay. And start video, here we go.
Yeah, there we go. Yes, brilliant. And you know, you
Right.
can always go back to your presentation if you like by restarting sharing. Yeah, we're going to to successfully manage that situation. So there is a first question by Norman. When do you expect exactly to resume drilling?
Ha. Well, if you could put a good word in for us, I'd be appreciated. There is, we have, it's a difficult question because we know that the JOIDES Resolution, the drill ship that we used, is not equipped, it's not technically able to go the 5 kilometers we need to expect to get down to, well, no, probably about 2.5 kilometers, 3 kilometers more we need to get down to get to where we expect to have something different. So the seismic boundary, the seismic Moho is at about 5 kilometers or so below the surface. So we can go deeper with the existing ship, but we can't go all the way with the existing ship. The Japanese also have a drill ship, and we're hoping that we can perhaps use that. That drilling ship has greater capability of getting deeper. But we also need to be exploring new technologies that can allow us to get deeper quicker, and it'll be a good couple of years at least, I think, before we have the opportunity again. We are putting our efforts in the moment into writing updates and bugging people on committees to allow us to have some more ship time. But unfortunately, the ship is also a long way away from us at the moment.
Very nice. Thanks a lot, Chris. Yeah, I also believe the big problem of these ships being located in different parts of the world is it's really expensive to move them around, right? Because they consume a lot of fuel.
I think it's slightly scary to think about the cost of these expeditions. I mean, the expedition we had cost us about $18 million, I think. And that is the same as having a big pile of £10 notes and just giving it across to somebody at this rate for 2 months. And that is scary. You can say, is it worth it? Well, you know, that's a value judgment. It's a great deal cheaper than any space science. It's a great deal cheaper than any satellite-based work. It's a great deal cheaper than anything to do with particle physics or anything like that. So, you know, it's some things you have to spend money in order to do anything. And I think that's one of the judgments. That is why we have an international consortium. So every country, or most of the major countries, then contribute a small part to being involved. So it's too much for any one country to bid for. But that's why we were very, very careful to make sure when we do have the ship, we use it properly. We don't waste time.
Brilliant. There is, I think, another question by Louis. I think, Louis, we've already addressed your question on how further deep into the mantle or below the ocean floor we should drill. If it's not the case, please, could you just rephrase your question and be a bit more specific? It would be greatly appreciated. Thank you. And there is another question. Could you perhaps elaborate a little bit more about slippery faults and when the process began and what the protolith rock is? I think it's in the context of the seafloor.
Yeah, so those huge faults that we found in the Atlantic and have a displacement of like 9-10 kilometers or so, and they basically take up all of the separation of the plates for a couple of million years at a time. We used those little baby sped rock drills, landed them on the fault surfaces and managed to drill some cores from the fault surfaces, which was quite fun. And we found that they were made of foliated, sort of basically layered talc. Talc is a hydrated magnesium silicate, and it basically forms from peridotite. You basically need to add a few little ingredients to it, but basically it's just mantle rock that takes up water in its lattice and turns into a layered rock, which is then very, very weak. So talc, as you probably know, is the weakest of all rocks, hardness of 1. And so once you form talc, then basically it's so much weaker than surroundings that it keeps slipping. And so you just slip and slip and slip because it's so much weaker than all the surroundings. And that's a remarkable property to it, but seems to be how it works. You make something a lot weaker than the surroundings, and you can just, it's just energetically easier to keep slipping on it than to do something else.
Yeah, fascinating. Do you think that this sort of slip events, they can generate earthquakes as such?
That's an excellent question. I could have fed it to you beforehand.
That's not prepared. That's not prepared.
Okay, all right, good. Over the last few years, we got funding, some colleagues and I got funding to do a seismic study of the very place where I showed the big seafloor fault. And we had a bunch of seismometers laid on the seafloor for several months at a time in an array, so we could actually triangulate on which bits were slipping and how. And it turned out that there are hundreds of thousands of earthquakes we documented in that period, localized along the faults. And these, excuse me, it turns out that the rock is the faults are so weak that actually they just sort of grumble and sort of growl along continuously, rather than sort of building up big stresses and then failing in a big earthquake. On those serpentinite bits and the talc regions, they just grumble away, and they're making earthquakes of magnitude 0, -1 that we were able to document. So it's a log scale in the Richter scale, or the moment magnitude scale. So these are very, very tiny ones. They're equivalent. We can document things equivalent to dropping a carton of milk off your worktop, and the amount of energy that's released that way you can actually detect, and we're finding that that's the kind of energy released on some of these features. It's remarkable. It
is, because they are really huge features, so they're really cool. Yeah, so there is another question and comment by Peter. So first of all, congratulations on your talk. It's actually very helpful for A-level students, as your work features directly in their new specifications. So it's really great that actually we have some geological topics embedded at A-level. That's really important, I think. And there is a question. So what is your best guess on the likely definition for the Moho on future Wikipedia posts?
That is also a very good question, because a lot of people, myself included, have been quite lax about what we mean by we say Moho. For petrologists, they still talk about the crust-mantle boundary, the boundary between gabbros and mantle prototypes. But actually, the Moho, the Mohorovičić discontinuity, to be strict, is a seismic boundary, and it's a boundary where there's a step increase to 8 kilometers per second p-wave velocity, below which is typical of the mantle. And so it is the boundary between something of lower velocity and the mantle. And so we should be clear when we're talking about the seismic boundary, and we should be clear about when we're talking about what we interpret as a lithological boundary between the crust and the mantle, or whatever. Okay, so I think we've shown that Wikipedia article is wrong, in the sense that it is not always the crust-mantle boundary. We don't know how applicable in how much of the ocean floor my serpentinite, our serpentinite seafloor is. Okay, that's the challenge, is to see if we can find a remote way, so we don't have to drill it everywhere to test between the two. In fact, we can do it if we look at the P wave to S wave velocity ratios and various other things like that. But the cost of actually doing that kind of survey is so expensive, you may as well just drill holes in it.
Yep, but still, I'm personally very much looking forward to seeing some direct constraints to better use the indirect geophysical data. Yeah, brilliant. So a question by Patrick. With the ocean floor turning over every 2 million years or so, where is the talc and serpentinite going? Is it eventually being subducted, and what mineralogically is their fate. So I think it's a question about the global cycle of plate tectonics.
Yeah, that's also an excellent question. I mean, it's more than 2 million years for recycling everything, probably 200 million years, probably for average age of subduction of ocean crust, or 100 to 200 million years. But the question is appropriate. Hydrothermal alteration, circulation of seawater through the ocean crust to help cool the crust down and create mantle lithosphere underneath. So you cool down the upper layer, the plate, not just at the ridge axis, but right the way out across the whole ocean basins. Water circulates through to extract heat. And what it does is it cools down the top part of the mantle underneath, which basically gets stuck to the base of the plate. Water is added to the ocean lithosphere, the crust and the mantle, by doing that along the kinds of faults that I identified and elsewhere. So the serpentinite seafloor has about 13% water in it. So the thoroughly serpentinized, thoroughly altered mantle has an awful lot of water in there. Eventually, when it gets down to subduction zones, that gets taken down into the mantle, and it's going to be subducted. It's going to be released into the mantle lithosphere and the overriding plate. And there is evidence, in fact, from a recent big study of the West Indies that those places where transform faults and fracture zones were subducted, were able to document they had much more serpentinite associated with them. So basically subducted more water in those places, and the lavas that are erupted above in the island arc are wetter. So there's a very distinct relationship between the serpentinite seafloor and the areas where there's more alteration and hydration of the mantle of the ocean lithosphere, and this so-called subduction factory, where we are recycling material. So yes, you carry it down into the mantle and it has a big real world effect. It's only now just being appreciated how much that's going to be happening.
Yeah, great. Thanks, Chris. There is yet, I think, about three questions to address. So there is a comment by Richard about a machine that he helped develop in the 80s. I'm not 100% sure what the machine is doing, and but in any case, please, Richard, if you think it could be useful to some of our research or some of our outreach activities, send an email to the Earth Engagement email address, which I'm going to show again at the end of this talk. Very good, and I'm trying to get back to the other questions. Yeah, so a question by Norman. So are conventional models for ocean crust still valid for some areas of the seafloor, or is everything in the end questionable?
That is also an excellent question. I think that at fast-spreading ridges, okay, the whole of the Pacific, we have the seismic experiments you can do on the ridge axis show that there's melt in the crust. There's some kind of magma body there. It's probably mush rather than a large cauldron of magma. But basically it's magma dominated. There's plenty of magma made there, and therefore the magmatic crust will likely be generated by something comparable to the mechanism. I wouldn't say the mechanism in the textbooks. The lower crust certainly it's much more complicated than the simple models for magma chambers. But yes, I think in that case you will make a layered structure with a gabbro, a sheeted dike complex, and an extrusive pillow lava sequence. As for slow spreading ridges that might be more magma rich, where you see pillow lavas on the seafloor and apparently a seismic crust underneath of a normal thickness, quite possibly, yes. Along strike there are variations, there are quite extensive variations. A colleague has done an analysis of some of the seafloor morphology and reckons about half of the mid-Atlantic ridge is probably dominated by magma, whereas about half is probably dominated by some form of serpentinite seafloor and attachment faulting and a complicated heterogeneous variable structure. So that's our best guess at the moment. And we can get certain things from seafloor surveys, but other things need sampling at depth in the third dimension.
Great, thank you. And I think that's the final question, and I think it's a great final question, not only for this talk, but probably for the GeoTalks series this year by Richard. So you say we have a lot to learn about plate tectonics, and you mentioned that many regard the mantle as liquid. Are you aware just how widespread this mistake is? I think we are. So, but Richard says he has had to correct the BBC bite size and the BGS on this, plus recently BBC Two Tropical Islands recently told us that magma comes from the Earth's core, which to us as geologists is a bit like saying the Earth is flat. Please trust us. So it's horrible, really. So how do you think we can eradicate these problems if now even the institutions perpetrate such errors?
That's almost impossible to answer, really. I think we all just have to play our part. As we can, which is why I'm very happy to talk in, to give talks like this. And it's going to be a bit at a time. But I think that the more we can demystify science, scientists aren't weirdo. Well, some of them are, but we're not all kind of strange creatures that are about to try to destroy the planet. There's a bigger issue here about knowledge and about information and stuff and truth and so on. But I think just education. It's just the more we can get people to listen and to be interested, then more the better. It doesn't help that mantle and magma sound quite similar. A lot of the undergraduates mix the two up, I think we just have to keep trying, keep picking them up wherever we can do. We do our bit when we can do, but we're pulled in so many directions we can't necessarily follow all of these things up when we see them. But the more you all do, the better. Then that's great. We definitely appreciate it.
Yeah, great. Yeah, thank you very much for spreading the word. I think that's the answer. We just have to spread the word and communicate and educate. And that was in part the intention of the GeoTalks series, just to try to bring in people around a webinar to talk about very fundamental things that we are researching. And it can be sometimes very technical when scientists and researchers try to explain what they do. Hopefully, that series has been basic enough, at least in some aspects, that it had the potential to show the general public that geology is not about very boring rocks that don't do much at first glance, but that ultimately it's related to a very dynamic environment. So our environment, our planet, and there are many things that we always experience or face in our everyday lives that are obviously directly or indirectly related to geosciences as a whole. So yeah, it's been really my pleasure to have you, Chris, today. So you've got a few other very kind comments, I think. So I'd like to reiterate that well, unfortunately, it's the last talk of this type this year. But the plan is to perhaps revive the series starting probably Easter next year for a few months. I'm going to share again my screen to show the email address that you could use to basically send emails of either encouragement or suggestions how you think we might do this a bit, slightly differently. We're always looking for constructive criticism. And yeah, I also need to mention that before the GeoTalk series, we had public lectures in the School of Earth and Ocean Sciences. And obviously there are some advantages in like the webinars because people don't have to travel And there are also some advantages in having like on-site public lectures. So the plan is basically to resume some of the public lectures as well, hopefully after the whole COVID situation. So we're hoping for a vaccine, and we hope that the situation next September or October, so in 2021, is going to be much better to resume the public lectures. But it shouldn't mean that we're going to totally stop the GeoTalk. So hopefully we're going to have the pleasure to see you again next year. So keep an eye on our events webpage, and we're also going to use social medias to spread the word. So I'm really hoping that we're going to have a chance to resume this next year. So again, thanks a lot, Chris, for that very interesting talk, and thanks all.